the material on the attack on LaRouche, and it was eerie because it was so similar to what's going on with Trump.
No coincidence.
And our organizer said, well, yes, in fact, some of the same people ran the operation. And this person said, how could it be the same people? That was 30 years ago. And our organizer said, did you see Robert Mueller in his testimony? It was the same guy, but they're pretty much finished, and they're also politically finished. But there are two operations. One is an inside job against the president to try and, which is being run publicly now by the British intelligence. They admitted it through their ambassador in the leaked cables that never really got revealed in the U.S., that they were trying to do what they called flood the zone and ensure that all the policy advice President Trump is getting came from British policies. And so that has to be dealt with, and this fight around the space program will help with that. But secondly, you have, and as part of that, the constant attacks on the president as racist. Somebody asked me yesterday if I had watched the Democratic debates. I said, no, I know they called him a racist, and they called each other racist, so I really didn't need to watch.
It's a word that doesn't mean anything anymore.
The debate. But what I had not seen, and what probably most of you have not seen, was the speech that President Trump gave at the Jamestown celebration of 400 years since the first independent legislative body on North America in Jamestown in 1619. Now, the day before he went there, he met with the niece of Martin Luther King. Her name is Dr. Alveda King, and some black ministers in the White House. And Dr. King came out of that meeting and she said, all this attack on Trump as a racist is fake news. But of course, the fake news never reported to you that she said that because they're too busy making up fake news. And I wanted to read you a section of what the president had to say, which they also didn't report. He said, in August of 1619, the first enslaved Africans in the English colonies arrived in Virginia. Today, in honor, we remember every sacred soul who suffered the horrors of slavery and the anguish of bondage. More than 150 years later, at America's founding, our Declaration of Independence recognized the immortal truth that all men are created equal. Yet, it would ultimately take a civil war, 85 years after that document was signed, to abolish the evil of slavery. It would take more than another century for our nation, in the words of Reverend Martin Luther King Jr., to live out the true meaning of its creed and extend the blessings of freedom to all Americans. In the face of grave oppression and grave injustice, African Americans have built, strengthened, inspired, uplifted, protected, defended, and sustained our nation from our earliest days. So that's from the president. And then, interestingly, given this whole scandal around the British, which the president is clearly very aware of, he ended by saying, one fact was quickly established for all time. In America, we are not ruled from afar. Americans govern ourselves, and so help us God, we always will. So a very interesting. Now, the kind of last gasp but very dangerous attempt to rule us and the world by afar is something that people tend to know as the Green Agenda or the Green New Deal, but is actually something far more insidious than even that insanity. It was named, there's an organization that was put together in Britain in October of last year called the Extinction Rebellion. This is not the 17-year-olds and 15-year-olds you see out in the streets. This was diplomats, professors, psychologists, and others. And it was modeled on Bertrand Russell's Committee of 100 from the 1960s, out of which was created the anti-war movement, which was not so much an anti-war movement as it was to create a counterculture of drugs and rocks, drug, rock, sex counterculture that destroyed the morality of much of the boomer generation. They're trying to use what is basically child abuse against these children. I mean, I remember when I was in college getting the first leaflet about the danger of the environment being destroyed and how everything was going to be, you know, desolate on the planet and something had to be done. This was, as you may imagine, quite a number of years ago when I was in college. But it scared me. And I was, you know, a college student and fairly well educated, and it scared me, and I started looking into it, and I fairly quickly realized it was bunk. But imagine, you know, you're a 12-year-old kid, and you're being told by your teachers, you're being told by adults that your parents have destroyed the planet and have created a circumstance where there won't be life on this planet in a dozen years unless industry is shut down, unless a lot of human beings are eliminated. That is child abuse, and these children are being unleashed, you know, against industrial civilization, including in terrorist acts. There was apparently a case this week where some of these, you know, Extinction Rebellion people glued themselves to doors in the Congress to prevent congressional work from going on.
Crazy.
We're very, you can imagine if they think that coal mining or chemical plants, we've had a number of chemical fires. They weren't created by any of these people as far as I know. But you could see, you know, terrorist attacks on chemical plants, on nuclear plants, on coal facilities, on other things. This is the kind of danger. Well, we defeated Robert Mueller and the Russiagate operation with the material we put out and the fight that we launched and triggered. This leaflet, Extinction Rebellion, British Green Fascism to Destroy Industrial Civilization, is the opening shot of a campaign to shut down this last-ditch fascist effort on the part of the British to control the world and make sure that instead we go into a new paradigm of industry, science, the Belt and Road, space program, everything Americans want to see occur. So let's have a few words from Lyndon LaRouche, and then we'll have Joel.
That we get certain people in Russia, China, and India, and the United States as a block of nations around which combined are sufficiently powerful as a combination to force the needed changes on a planetary level. In other words, by net changes, I don't mean jobs. You know, the idea of giving somebody a job to rake leaves is not exactly an economic development program. What we need is production jobs. We need nuclear power. We need a national rail system. We need a space program, a real space program, revived. Because we don't have factories of any significance anymore. We shut them down. Especially under George W. Bush Jr. and this thing there. They shut it down. What happened to the automobile industry? What's happened to the aircraft industry? Go all to all the high-tech industries we had. What happened to them? They're gone. We still have the knowledge of that technology, but we are losing the people who are able to practice it. We have jobs, yes. What are jobs worth? Raking leaves? You build a world by raking leaves or doing social work? No, you build industries. Today, that means, for example, nuclear power. Technologically, it's impossible to develop the population of this planet without nuclear power on an extensive basis. And that's not enough. What you have to count on is higher energy flux density. You have to increase the energy flux density of the power in the hands of labor. If you can't do that, you cannot achieve the productivity necessary to save this nation and save the world. We talk about a vast program of this. We have to go to space. We have to undertake the industrialization of the moon. Because if we don't do the industrialization of the moon, we can't get to Mars. And if we can't get to Mars, which may take several generations to do that with human beings, we can get there already with the slow craft, 300 days or something like that. But if you're going to bring human beings there, you've got to talk about a mere few days between Moon orbit and Mars orbit. And that involves some problems. But we pretty much shut down NASA, which was the mission orientation for that sort of thing. Now, the Mars project is necessary for humanity in the sense that humanity functions on the basis of something about human beings which animals don't have. The animal world has creativity and the development of species, new species, varieties, and so forth. Even the non-living world undergoes development. The universe, the physical universe, is undergoing development all the time. But it has no will to develop. It has no knowledgeable will to choose to develop. It develops because the creativity is built into the universe. Man is different. Man has the willful creativity to shape the universe. And therefore, man cannot function without having the inspiration to use that ability, that creative power, to achieve higher goals than are currently practiced. For example, we have a planet of very poor people, in Asia in particular, in Africa, a terrible mass of poor people. We're running short of many resources. We have to create new resources. We have to increase the productive powers of labor of the existing population. We have 6.7 billion people now on this planet. We're headed towards 7. We have to progress to meet that challenge. We have to inspire our people each in their own culture to take this mission orientation for mankind as their responsibility. In order to challenge people, what do? Well, you educate them. And you adopt missions which make goals, higher goals, clear to those people. And children say, I want to do this. We had back in the 1960s, even into the beginning of the 70s, you had children who were saying, I want to go into space. The moon landing program of NASA was an inspiration. The Russian-Soviet program was also an inspiration to the planet. You have to have these kinds of goals of missions for mankind to use his creative powers to raise humanity to a higher level of existence. You have to talk to your children and grandchildren about this kind of goal. And it's only when you get their imagination stirred that they become creative. And without the bestirring that creativity, mankind does not progress. And that's what we used to say about the United States. We were a nation that was committed to that sort of thing. What we did under Franklin Roosevelt was an example of a nation which had been crushed under a legacy of Teddy Roosevelt and Wilson and similar types of scoundrels. We were almost destroyed. But we rebuilt, and facing the challenge of the war in Europe and the challenge of unemployment, the challenges here, we mobilized our people to create a machine which is the most powerful machine the world had ever seen. The machinery of the United States, which was deployed for World War II. The intention was to continue the development of that machine in the post-war period, not for war purposes, but for construction of the planet. Roosevelt had a clear plan for this thing. Truman had a different idea. Truman kissed the butt of Winston Churchill. And we've been getting the backlash from that ever since. We destroyed most of our capability. We destroyed our industries. We just shut them down. We had all kinds of projects for post-war projects which would have led to great achievements. And we shut them down. Nuclear power was one example of this thing. It was feasible in principle. Sometimes it takes you a couple of generations. Once an idea is clear and feasible, it may take you 2 or 3 generations to actually bring it online as effective. But the way in which to organize mankind, 2 questions. First, we have to understand culture. We have to understand national cultures in particular. Because national cultures embody, within the use of language and other things, embody the heritage bits of knowledge and experience of past generations of that people. Therefore, you cannot go into a country and say you can't create a Tower of Babel, a one world economy. You have to use the culture of the various cultures of the people as your mobilizing force. Because it's in their imagination which is associated, the powers of imagination associated with their culture, in which they are able to mobilize creativity. So you want to create the opportunity for upgrading them through fostering the benefits of their own creativity and inform them of the objectives that other people are achieving, which they may copy and build upon. So you need a system of sovereign nation states, of sovereign peoples, different cultures, each with its own sovereign expression, and the unity of these people for a common purpose, the purpose of humanity. To do that, you must stir the imagination, the powers of the imagination of the people. And what means reach to space. We're going to Mars. It will probably take us 3 to 4 generations to do that, to solve the scientific problems that are involved in overcoming very high speeds of, or rates of acceleration in interplanetary travel, which is required for moving mankind around. And this is not easy, but we know we can solve the problem. We just have to go through the steps of solving it. Take us 2 or 3 generations or more, but we'll get there. But as long as we inspire our young people, especially younger people, to look at their adulthood, we've got people in their 20s, they're going to be functioning probably for 50 years to come if we can get Obama out of office. He doesn't seem to be in favor of that sort of thing. And they should be looking forward to what they're going to produce within their own lifetime as benefits for humanity of which they will be proud. It's a span of about 60 years, approximately, that they think in terms. Most people think that way. They live that long. And when people can find a purpose in their life, in the sense that what they are doing now, what they are preparing themselves to accomplish, will lead within their own lifetime to the foundations of something much better than they have today. That's when you can capture and sustain the imagination of a people in its own culture. And when people are united, even they have different cultures, if they're united by a common purpose to do this, to cooperate to do this, then we have peace among nations on this planet. And that should be our goal. It should be our goal now. What seems impossible to small-minded people are the ideas that are necessary to get out of the pit that we're in today.
Now DeJean will tell you about how we're making progress toward that goal.
Well, we got rid of Obama, so it's in the last 10 years. With the 50th anniversary of the Apollo 11 landing and the announcement of going back to the moon with the Artemis project, there's been renewed optimism. And if you've watched any of the coverage in the last few weeks, you notice that a lot of the reason for going back to the moon is, since we've been there 47 years ago, we've discovered that there's a lot of water ice on the moon, especially in the south polar craters inside these craters where there's no sunlight ever. So you have this frozen water ice, estimated at about 1 billion tons of water ice. Now, what's the big deal about ice? Well, their reasoning is that, well, if we have ice, we can have water, because water is very heavy. If you've had to carry 5 gallons of water up a few flight of stairs, you know how heavy water is. But imagine having to carry water to the moon to sustain your settlement there. So if we have water ice on the moon, we can use it for the settlement, for water. If we do electrolysis, we can break it down into hydrogen oxygen for breathing. And hydrogen and oxygen also happens to be the best chemical fuels for rockets. And that's part of the way we got to the moon. And then they go from there to say, well, we can have the moon as a gas station so that we can go beyond the moon to Mars. But then you have to stop and think, are we going to use the same methods we use to go to the moon, which takes about 3 days flight time, to go to Mars? Now, there are a few constraints there that LaRouche touched upon in the video. Now, the shortest, the closest distance between Earth and Mars, and if you just picture, Mars takes about 2 years to orbit the sun, and Earth takes 1 Earth year. So during that 2-year span, there's a configuration where the Earth and Mars are closest. The closest is about 35 million miles, which is 140 times the distance to the moon. The moon is 240,000 miles from the Earth. Now, if you're going to send a spaceship to Mars, the shortest time, where it's the shortest distance, is about 6 months. Now, that's not a problem for the probes we've sent out there, like the rovers and the various orbiters. That's fine. But if you were to send human beings to Mars in 6-month time frame, what they will suffer with the exposure to microgravity and cosmic radiation, because even at the International Space Station, it's still within the magnetic field of the Earth, so they have protection from most of the cosmic rays, the solar flares, the solar wind coming from our own sun. So LaRouche, for over 30 years, has called for using fusion-powered spacecraft to accelerate, and he briefly mentioned it in the video. Constant acceleration, 1 Earth gravity, massively reduce the flight time. Now, he's called for this for 30 years, and some people would say, well, we've been talking about fusion for 30, 40 years. It's been 10, 15 years away, and it's still 10, 15 years away. So, but we have 2 examples to look back on. If you think back to 1960, and you were to ask yourself, well, how long will it take to get man on the moon? Before Kennedy's speech, that time was infinite. Another example is if you look back in 1905, Einstein discovered that there's an equivalence between mass and energy through his E equals mc squared. Now, it took another 34 years before a Austrian physicist, chemist, confirmed that in experiments conducted in Germany by Otto Hahn, we were getting fission, or the splitting of the atom. And the way she figured it out is that she figured out there was an increase in energy, which was exactly what Einstein had predicted 34 years before that. Now, during World War II, from the spring of 1942, under the Manhattan Project, which was launched in December, a day before Pearl Harbor, December 41. But by the time they built the facilities like Los Alamos and Oak Ridge, Hanford, it was springtime before they really got cracking on it. So from spring of 1942 to July 1945, we not only designed built, we tested an atomic device in just a little over 3 years. So getting back to going to Mars, again, if you were just to use your best chemical propellant will get you there when the planets are aligned in about 6 months. So how are you going to get 1g acceleration? So I'm going to touch on a few things, but just to think about distance. Distance is the velocity times the time. Now that's for constant velocity. So if you're going down the highway 60 miles an hour constant, you get down the highway 60 miles. In space, once you accelerate to escape velocity, most of the time the spacecraft is coasting to its destination. So how do you accelerate and decelerate? And Mike, I forget that. Do you have an eraser and a marker?
Oh, well, the problem is the board is behind it.
Oh, that's right. It's not for the board.
Right.
I wanted to demonstrate gravity.
Great.
Or you have a gold bar and
Well, drop an apple.
yeah, you got an iPhone. Anybody want to use an iPhone?
Here. Here's an eraser, there's a marker.
All right. Well, you might have seen some of this during the coverage. One of the astronauts did an experiment on the moon, and it wasn't how far you could hit a golf ball. That was another experiment. But you probably heard of this experiment. You think that on Earth everything is accelerating, including you, at 9.8 meters per second squared every second. So a lot of times people in the past thought, well, if you have a bowling ball and a feather and you eliminate the effects of air resistance, which is going to hit the ground first? Imagine I had a bowling ball and a feather and I was on the moon, so there's no air resistance. And I had my oxygen tank and I dropped it, which would hit the ground first?
You guessed the bowling ball, because it's heavy.
Well, you guessed wrong.
Just throw that out.
Because everything is accelerating at the same rate, at 9.8 meters per second squared. So if I take this eraser, which is fairly light, and this marker, and which one hit first?
They hit at the same time.
Same time. Now, have any of you seen this experiment that was run on the moon by one of the, I think it was Dave Scott.
Dave Scott, right?
Yeah,
That's right.
Apollo 15.
Right.
He, during his excursion on the moon's surface, he brought out of the lunar module a hammer and a real feather. I think it wasn't an eagle feather, but it was. And he went through. Now he credited to Galileo, but I'll overlook that. But he went through and said there's no air resistance, which is going to hit first. He did the same thing, and the hammer and the feather hit at the same time. So things are accelerating at 9.8 or 32 feet per second squared every second. So if you accelerate a spacecraft at 9.8 meters every second, by the time you reach 1 day, now remember, every second you're accelerating. So distance traveled is acceleration times the time squared. And accounting for, you're going to be accelerating and decelerating. So it's 1/2 acceleration times squared. So after 1 day's acceleration at 1 gravity acceleration, Can anybody guess how much distance you would have traveled without using your calculator?
A lot.
Well, in one day at 1g acceleration, you'd travel over 22 million miles.
Wow.
And what you do is halfway to Mars, you turn the spaceship around and you keep the engine running so that while you were going 1g acceleration, now you're going 1g deceleration. Because the idea is to get to Mars, not just fly by. Because
Not to hit it and get splashed.
oh yeah. Because you're not doing target practice. Because if you keep accelerating, you'll hit millions of miles an hour. So you just fly by. So you want to decelerate. Now the advantage is that the microgravity, it's like you're under no gravitational field. If you're in orbit, you're falling, you're still under the gravitational pull of the Earth, but because you're traveling at 17,500 miles an hour, so the centrifugal force equals the gravitational force, so you're weightless. And under those conditions, your bones become brittle. It's like you get osteoporosis. And your muscles atrophy, and they have some eyesight problems. So if you look at the effects of microgravity, you don't want a crew getting to Mars and being incapable of getting out of the spacecraft.
Yeah.
Because you may have seen the coverage. There was a cosmonaut when the Soviet Union disintegrated. They had a space station up there called Mir, and they had a cosmonaut up there, and for some reason they couldn't get another spacecraft up there to bring him down, so he got stuck up there
Oh,
for about a year.
really?
And he had enough food, he had enough air and water.
Yeah.
But when he got back, when he left, it was the Soviet Union. When he got back, it was the Russian Federation.
Yeah.
So he landed in a different time zone, country, and everything. But when they got to his capsule, he was literally incapable of walking
Really?
because of the atrophy of his muscles and the bones had weakened. He was alive, but you couldn't function on Mars under those conditions, even though Mars is only 38% of Earth's gravity, while the moon is 1/6 of Earth's gravity. Still, you're not going to have a functioning crew when you get there after 6 months. So we have to have an energy-dense form of propulsion. And the candidate that LaRouche, Kraft Erica, and others, anybody who's looked at this says we have to have fusion-powered propulsion. So LaRouche wrote a whole document on this in '86. We've republished his writings. He had a whole quarterly report on this in the first quarter of '87 with all the detailed calculations. And he, in '87 and '86, he even talks about using helium-3 on the moon as one of your fusion fuels. And he goes through the weight of the spacecraft, the acceleration, the time. The closest you can get to Mars in 2 days. If they're not in the close orbit, you can get there in 10 days. So instead of months, we're talking about days of travel time. And obviously, if you can master fusion for your rocket, then you can figure out how to use it for your energy. And in his various papers, LaRouche estimates that your settlement on Mars is going to need 10 times the per capita energy that a settlement or an outpost in Antarctica needs.
Wow.
And you just don't want an outpost, you want a whole city, and he has that whole city development plan. But what I'm going to look at is just the latest developments in fusion propulsion. Now, we're not quite at 1G yet, but the first fusion rockets will probably be maximum 1/10 gravity acceleration. But still, that would cut the travel time to Mars in half. So you get there in 3 months. But obviously, this would be the first step, then we'd have improvements. And like Lou says, within 20 years or so, we'd be prepared to actually have a full-fledged program to have settlements on Mars. But in the meantime, we could use that increase in technology and the control of thermonuclear fusion to solve any energy problem we have here on Earth. Now, the first one we'll look at is, we've actually visited this company. It's near Princeton. It's called the Princeton Satellite Systems. They have a new division now called Princeton Fusion Systems. It's a small company, but they have had various contracts from NASA, the National Advanced Concept Contract, and they just received a contract from the Department of Energy, which has an advanced research project agency, not for defense, but for energy. And they're looking at using their, what they call direct fusion drive system, and converting it for a portable 10 megawatt power system that you can use anywhere on the planet. And the head of the company, actually, he's a real movie buff. He says that if you look at the Back to the Future, one of the cars was powered by a fusion engine. And he says fusion power, and we can actually operate a crew carrier, not a tank, crew carrier with a fusion engine, and you wouldn't have to spend the money on diesel and all that. So, is this the first one you have?
Yeah.
All right. So, they are actually looking at using deuterium, which you can get from seawater, and helium-3. Now, the helium-3 they're using, helium can come from the moon, or you can get it from old nuclear bombs. Because the tritium, the H-bomb, this is called, has deuterium and tritium. And tritium has a half-life of 12 years, and it decays by shooting out a beta, or an electron from the nucleus. It decays into helium-3. So we have a little bit of helium-3 on Earth from old warheads, and from, you can get it from natural gas fields, you can get helium from there, and there's a certain ratio of helium-4 to helium-3. But in this system, they have, instead of one of these huge tokamaks, they're using what's called a field reverse configuration to confine the plasma. They heat the plasma with radio frequency beams, and they get the deuterium and the helium-3 to fuse, and they have a way of getting energy out of that to run their spacecraft. But they're also using the reaction products as part of the thrust. So, which end is the thrust end? I was speaking
On
of
the left.
on this side.
Yeah.
All right, it's good to know which way the thrust is going. So, if your thrust is going out that way, you can be accelerating your spacecraft. And if you have a cluster of these rockets, you can actually push a habitat from Earth orbit or Moon orbit to Mars in something like 3 months. Now, the amount of their contracts, if we're talking about $1 million here, $1 million there, I mean, we're talking about pittance. So their work is ongoing. Now, there's another company, and you put the other one up there,
Yeah.
slightly larger company. You may have heard of Lockheed Martin. The largest defense contractor Now, that was as of last year. Sometimes they switch. But Lockheed Martin has a division called the Skunk Works.
Skunk works?
Yeah, there's a whole story behind that. I won't go through it now. Evelyn can tell you about that. But they actually built the first jet for the U.S. Army Air Corps at that time in the 1944
Wow.
period. And they had a separate division because their main division was making Lockheed propeller combat aircraft. And they didn't want to interrupt the production line, so they had this separate unit to work on this fancy new technology, jet engine. They built the U-2 spy plane. They built the Mach 3, or 3 times the speed of sound, SR-71, called the Blackbird, which still has the world record for speed as far as a jet. Not a projectile, but manned aircraft. So their division is working on a 100 megawatt compact fusion reactor, which you can see in some of the outline there. But again, they're containing the plasma in this cylinder. They're heating it up, and they have different. This one uses, instead of helium, it goes back to tritium, and they have to have a heavy lithium blanket around it to absorb the high energy neutrons. Because the problem with tritium and deuterium is that the product you get from that is a helium-4, which is a charged particle called an alpha particle, and a neutral neutron. And most of the energy is in the neutron, so it can hit the walls, and you can't direct it, because you can't influence it with magnetic or electric fields. But you can use the energy of the neutron to, once it hits this lithium blanket, you can run coolant through that blanket and extract the heat for a heat exchanger. You can run turbofans, you can generate electricity. And the neutrons, some of them that hit the lithium, cause a reaction in the lithium where it creates an alpha particle and it creates more tritium. So you can keep the reaction going. So this they've been working on for at least 5 years, and it's ongoing. And they promised a prototype at the end of the year. So keep your money for Christmas if you want to get a 100 megawatt fusion reactor. You may be able to get it by Christmas. I can't promise on that.
So here's the plasma, Joel, the plasma viewer.
Okay, can you see the cylinder and the?
No, we don't see the cylinder. It's just the plasma and
Coil.
the coils.
Okay, well the coils keep the plasma from spilling out, and it heats the plasma so you get your fusion. But this work is ongoing. Now, there's a facility in California called the National Ignition Facility. Can you put that one
Yep.
up? Is that the outside or?
Outside.
Okay. And I don't know if you can tell the size. Can you see the mountains in the background?
Yeah.
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 This is about a 3 football field
Wow.
like facility. This is the most powerful laser in the world.
Really?
And they actually use this facility for filming of one of the Star Trek movies. They used the target chamber in this part of their production. But in a few billionths of a second, it can produce a laser that is thousands of times more powerful than the entire electric grid of the United States. So they store the electricity in capacitor banks, and they release it, and then they have 192 lasers focus in on a small little tablet that has cool deuterium and tritium in it.
Wow.
Now, can you show the
Yeah.
target chamber?
Yeah.
Is that a human being on the side?
Yeah.
Yes.
Okay.
I don't think it's Michael Stater, but
Okay.
what do I remember? But you can see the size. It's about a 10-meter chamber, And they have all sorts of instruments lining the walls because they measure what comes out. I don't know, can you see the pedestal that's sticking out? I'm not sure how close, but essentially you have a pedestal thing, and they put this little aspirin-sized capsule that has the cool deuterium and tritium, and they have 192 lasers come through after being amplified, come through various mirrors and are all pointed at the little capsule. And now they're using a method where they're not hitting directly the capsule, they hit what's called a hole chamber. And they produce soft X-rays from the chamber, and the soft X-rays compress that tablet. And they can compress it so that the deuterium and tritium will begin to fuse. And they've actually measured, and the way you can tell how many fusion reactions you have is you measure how many neutrons come out of this little tablet. And over the last year, they've measured something like 19 quadrillion neutrons coming out of just one plasma. Now, this is billionths of a second. And they measure this. Now, the problem they're having is it's still, you put more energy into the laser than you get out from the reaction. But they're coming up with new schemes. They've now achieved what's called the alpha heating, where the reactions from the fusion create helium alpha particles. The neutrons go flying off, but the helium stays within the capsule and heats up the plasma, so it keeps the reaction going. But it's not quite ignition, but they're working on that. They have a new scheme where they're going to use not only the laser, but they're going to use a few of the laser beams to excite a coil near the capsule to create a magnetic field, so that you create the plasma, then you create a magnetic field, and the field will contain the plasma, so you can increase the fusion rate, so you can get closer to ignition and eventually close enough to break even. Now, if you look at the report that the Executive Intelligence Review put out in the first quarter of 1987, there's a whole scheme of using a type of laser where instead of one shot, and they do about one shot a day, to get a rocket out of this, you would have to get 100 shots a second. And what in the report is that if you're able to do that, you can get a rocket that can produce 1 trillion watts of power. And that would be more than enough to accelerate one Earth gravity to go to Mars. Now, obviously, we got to shrink this thing. But once we get ignition, and we're getting close, and this facility has been operating for about 10 years now. Now, they're not using it just for fusion research. The actual reason for this facility was to simulate detonation of H-bombs. And they wanted this because there's a test ban treaty. We're not allowed to test nuclear bombs. Maybe if we ship them to North Korea, they can test it for us. But they use this to simulate the interior pressures and temperatures in stars, in planets like Jupiter, Saturn. So they have all sorts of experiments going on here. But their most important function would be to get a breakthrough on what's called inertial confinement fusion. Again, this is still using deuterium and tritium. Now, you may have heard, can you put the
Yeah, there you go.
Wisconsin? The University of Wisconsin has a fusion technology institute. And in a paper now be coming out, I put a link to Marsha Freeman interviewed the head of this lab, Kolsinski. and she interviewed him in 2014, but she's been in touch with him for over 30 years. And Harrison Schmidt, the geologist who's on Apollo 17, is associated with this Wisconsin Institute. And in the mid-'80s, he's the guy who said that, well, we have these samples, let's see what's in them. And because of increased technology, they were able to detect the samples that the Apollo astronauts brought back from the moon. Once they were examined again, they found that there was helium-3 in the lunar soil at a few billions parts per billion. Not a huge quantity, but estimated that there was over 1 million tons of this helium-3 isotope in the lunar soil. So this University of Wisconsin has been working on methods of how to mine helium-3. And you may have heard that the Chinese are looking at this, the Indians are looking at mining helium-3, the Russians, and it's time that the US can get in on the act. Because if we were to have helium-3 fusion, there's enough helium-3 on the moon that we could run Earth's fusion generators for over 1,000 years.
Wow.
Now, obviously, you're not going to keep the same rate of energy production, but it just gives you the scope of what's available. And anybody who says we've limited our resources, well, what was oil 150 years ago to a farmer?
No use at all.
Just
It
tar.
was a waste product. And what was uranium before the Manhattan Project?
Just a rock.
They use it for painting, for stained glass and colors. And it's very heavy rock. So what's helium-3? Well, helium-3 today, you can use it for laughing gas. But in the right configuration, you could use it as a fuel for fusion. And back a couple of weeks ago, one of the students of Kulczynski, I don't know if he was a direct student, but he studied in Wisconsin, Aaron Olson, gave a video message to our conference in New York City on July 20th. And he went through his proposal. Essentially, what you want to do, you gather up the soil, you heat it to over 700 degrees centigrade, and you can distill the various gases that come off of it. And so you could distill the helium-3, cool it, liquefy it, then you could use that either on the moon or bring it back to Earth. And it was estimated that one cargo full, if you imagine the space shuttle, the cargo bay, you fill that up with liquefied helium-3, that would be enough fuel to run the Earth, all of the power plants on the Earth, if they were all fusion power plants. We're talking about terawatts, trillions of watts of production. Much more than the windmills in West Texas.
And the solar panels.
You could run, oh yeah, much more than the solar. You could run the entire Earth for a year just with that cargo full of helium-3. And it's estimated that if you have 66 kilograms of helium-3, it's about 130 pounds, something like that. You could run a 1,000 megawatt plant, fusion plant, for a whole year. So it's very energy dense. So a few kilograms in one of these fusion rockets, especially the one from the direct fusion drive one from Princeton, you could have enough fuel to send a probe out to Jupiter or out to Pluto even, and get there in half the time. Now, this is not 1G acceleration, but it's constant acceleration. You can get to Pluto, and instead of flying by, you could have enough energy to break and enter into orbit around Pluto, send a lander, powered the lander with basically laser beams to hit the solar type cells. You keep the lander going and have enough power so that you can communicate and send the data at very high speed back to Earth.
Wow.
And to give you some idea, the New Horizon that went by Pluto in 2015, and then it went by this other frozen asteroid just around New Year's. It's still sending data from that flyby. Now it's just coasting, so it doesn't have, it has enough energy to re-steer itself, but it doesn't have enough energy to break and enter orbit. It's sending data back at the rate of 1,000 bits a second, which is what your old computer modem could do back in the mid-'80s. But if you have enough power, you can send data back at a much higher rate. Still the same speed of light, but much higher data rate. So if we look at what's going on with the Princeton and the Princeton satellite systems and fusion systems, they work very closely with the Princeton Plasma Physics Lab right next door in New Jersey. If you look at the defense contractors, Lockheed not only builds the F-35, but it's also built many of the probes, like the Juno probe and I think the Phoenix probe and a lot of the space probes, so they have a space division. If we were to focus a small portion of the defense budget, and we have these companies that already work on defense systems, and increase the funding for something like their compact fusion reactor, combine that with the work of the national laboratories, where you have all the national laboratories, Lawrence Livermore, Los Alamos, Oak Ridge, they can all be working on this crash fusion program. And we have already an international consortium called the International Thermonuclear Experimental Reactor, which India is a part of, Russia, China, the US, the European Union, and I think they were thinking about inviting Iran.
Yeah, they're part of it.
So, yeah, they could be, we should invite North Korea too. I mean, they can build stuff. But if you look at this international collaboration, which is already going on with the space station, with the thermonuclear experimental reactor, with the recent Event Horizon telescope, so we have a model of international collaboration. And if we use the example of the Apollo project, where, again, if you imagine in 1960, we couldn't even get a satellite into orbit. If you remember in 1958, Sputnik had launched in October '57. And all it was about 180 pounds, and it was sending a beeping signal. So people were so paranoid. But it sparked the creation of NASA. But NASA was created, and we were rushing to get a satellite to match the Russians. And the first launch of the Vanguard, it went up about a foot and splashed. All the headlines were Splatnik, Flopnik.
Yeah, right.
And it wasn't until they brought the A-team with von Braun, we finally got a satellite in orbit. But if you look at the distance we went from 1960, 61, where the most powerful rocket had about 100,000 pounds of thrust, to the F-1 rocket engine that powered the Saturn V. Now the Saturn V had 5 of these engines, and each F-1 engine had 1.5 million pounds of thrust. So if you go to the Houston Space Center, you look at the capsule that took John Glenn to orbit, and you look at, they have this whole rocket park, and you compare the Redstone rocket that took John Glenn into orbit, and you compare it with the Saturn V, which is it's on its side. But you look at the size of these engines, and it goes through what the fuel rate was. A mere 8 years from 1961, we not only tested the Saturn V, we tested the lunar lander, we put man on the moon in 8 years from when Kennedy said we choose to go to the moon. From 1961 to 1969, 8 years we went from Flopnik to Apollo 11. And the power of these rockets was increased over tenfold. Now you compare it to what we've done in the last just 20 years. One of my brothers reminded me that we went to see the last space shuttle launch, the Atlantis, in July of 2011. From 2011 to today, we still can't get to low Earth orbit without having an agreement with Putin and being nice to Putin to get up to the International Space Station. So 8 years we went from low Earth orbit to the moon. Now we can't even get to low Earth orbit. But with the revival of the moon program, and eventually a Moon Mars program, we're now finishing the building of the Space Launch System. We're coming up with new ways to have a lander to get to the moon. We're looking at the South Pole for the water ice resources. But again, that's fine to get back to the moon by 2024 and to start a settlement there. But to go beyond that, to get to the moon, we're going to have a leap, a technological leap. And like LaRue said, we don't know all the answers. We didn't know all the answers back in 1961. And without the Apollo project, if you look at what it would take, we still would not have been able to get to the moon by today without a crash program. The same thing with the Manhattan Project. There were all sorts of experiments on getting energy from the atom, but without a crash program, we would have never mastered fission. And right after we mastered fission, we developed nuclear thermal reactors to power submarines, aircraft, and eventually the commercial nuclear program, which has been heavily sabotaged. But without a crash program, we're never going to get fusion off the ground. We have all these experiments, but we need to accelerate. And if I may paraphrase JFK, we choose fusion because it is hard.
I have a question.
Yes.
How many people worked on the Manhattan Project?
There were thousands.
400,000 at the peak.
Really?
Well, that was
Directly and
the
indirectly.
Apollo project.
Yeah, I'm sorry.
But there were thousands. Have you ever read the book Atomic City
Not yet.
about Oak Ridge? Well, a lot of people worked at Oak Ridge, and Oak Ridge was just farmland in 1942.
Mud.
Well, it was mud when they were building the. But the head of the military head of the Manhattan Project, General Leslie Grove, came to the area, met with the senator from Tennessee, and this was during wartime. So he said, "Okay, we want this area, and we want it in Tennessee because we don't want it on the coast where it could be vulnerable to enemy bombing. You know, they were real paranoid back then." And they built this whole facility in a matter of months, and it was a totally secret. It wasn't even on the map until after the war. And a lot of people working there, they have this book, The Girls of Atomic City.
Yes.
And most of the people working on the program had no idea what they were working on. What they were working on was, how do you increase the concentration of the fissile, the isotope that will split U-235, how you increase that ratio to over 90% from just natural uranium ore. And they just didn't have one path. They had a whole nother facility in Hanford, Washington, where they were bombarding uranium-238 with neutrons and making plutonium. Because plutonium is a man-made element by neutron bombardment. So they had enriched uranium, plutonium, and then they had a whole other facility in Los Alamos, which they basically took over a Boy Scout camp. And they had all the top scientists. And there are a lot of funny stories where the scientists want to openly collaborate. And the military guy said, no, we got to have compartmentalized, need-to-know basis, because this is a secret program. And there was a huge fight, and eventually Oppenheimer, who was the scientific leader of the project, convinced the military that without collaboration, you're never going to get progress in building what they call the gadget, the device. So it's an example of what can be done with concentrated crash effort. So I don't have the exact numbers, but there were thousands of people involved. And most of them who were not the top scientists or the military people had no idea what they were working on.
Joe,
Yes.
just to mention, we did get fusion in terms of the bomb.
Oh, yes. Yeah, I forgot to mention that. Yeah, Edward Teller, who by the way, was a Hungarian immigrant, like a lot of these scientists. And he was a big advocate of what he called the super, because he figured out that what you needed for fusion is you needed a lot of compressed high temperature so that you can get these pesky little elements to fuse. So he came up with the idea, you use the atomic fission bomb and you have a special chamber called the Hallraum again. And it irradiates the walls of this chamber, and it creates what's called soft X-rays, and they impinge on the capsule that contains the deuterium and the tritium, and you get fusion. So we've mastered the quick release of uncontrolled fusion, and that was tested in November 1952. And to give you a comparison of the increase, the first atomic bomb over Hiroshima was 14,000 tons equivalent of TNT. The first test of a hydrogen device, now it was a little like the National Ignition Facility. It was about as big as this building, or at least this room, 2 stories up. So it wasn't something you could fit in an airplane, but it was a test device. It went off at 1,000 times more energy release than the atomic bomb. So we know how to produce fusion. The problem has been how you contain it, how you control it, so that you can have useful energy release. You don't release it all at once. And we know nature has figured it out because all the stars in the universe run on fusion. Anybody else?
Can you say something about the fusion reaction in terms of the particle physics of it? How does that work?
Well, I'll take deuterium and tritium. Now, deuterium is an isotope of hydrogen. So regular hydrogen is one positive nucleon, 1 proton. Deuterium has 1 proton and 1 neutral element, neutron. And it has one electron orbiting it. But if you create a plasma where you heat it to thousands or millions of degrees, that's Siri coming in. But usually the positive charges repel each other, like the same poles of a magnet. But you overcome that and they fuse, so you take deuterium and tritium, which has, it's an isotope of hydrogen with 1 proton and 2 neutrons. And you combine them, and what happens is that, so you have 2 plus 3, and you think you get 5. But that's not how it works in nuclear physics. You get 2 plus 3 equals 4.95. It's a little less than 5. So there's a little bit of mass that's missing. And if you take that missing mass and multiply it by the speed of light squared, which is 90 quadrillion times, that little bit of mass will give you a huge amount of energy. And that's the magic of fusion. It's more powerful per nucleon than fission. So the problem with deuterium and tritium, like I mentioned, is that the product you get is that from that fusing, you get one product which is called an alpha particle, or the nucleus of a helium, which has 2 protons and 2 neutrons. So that's one product. But most of the energy is taken out by a neutron. So you still have 5 nucleons. You have an alpha particle and a neutron. But the atomic weight of the reaction products is, again, less than 1% less than what you started with. And that difference is the energy release. Now, that neutral particle shoots out. You can't control it with magnets or electric fields. But you could use that neutron. That neutron can accelerate further reactions. Now, the good thing about helium-3 is if you replace the tritium with helium, and it has the same atomic number, weight number, as tritium. So 3 nuclei. But this time it has 2 protons and 1 neutron. And you combine it with the deuterium, and what you get out is an alpha particle, or a helium-4 nucleus with 2 protons and 2 neutrons. And instead of a neutral particle, you get a proton. So all of the products are charged particles that can be controlled by those magnetic fields you saw in the various reactors. So you can contain it, you can create electricity directly by just the flow of these charged particles, or you can use these charged particles as your thrust for your fusion engine. And the density of the fuel is 1,000,000 times greater than any combination of chemical reaction.
What is the half-life of helium-3?
Helium-3 has a long, it's fairly stable. I don't remember the exact half-life, but it's fairly stable. Because the sun in its core, the sun is still mostly hydrogen, like most stars. And in its core, at the surface, it's about 10,000 degrees Fahrenheit. It's going to melt your capsule if you try to land there. But at the core, it's millions of degrees, like 15 million degrees centigrade.
Man.
And because of the mass and the heat, fusion takes place in the core of the sun, and it produces helium-4 and helium-3, and eventually those products get to the surface, and some of them are released into the solar system, And it's that helium-3 produced in the sun, which has been spraying out there for 4.5 billion years. It's estimated that the moon has been hit by 500 million tons of helium-3, and most of it bounced off or didn't stick to the soil. And about 1 million tons of that is in the soil. Whereas on Earth, we have about just a few thousand tons tops.
And it's believed that it's more abundant on the far side of the moon, is that right?
There's some speculation to that. Again, a lot of this, we know, we have an estimate of what's up there by the samples that were returned to Earth 47 years ago.
Yeah.
So the half-life is at least more than 47 years. But it's I forget the exact number, it's probably billions of years. Because the half-life of uranium, people think it's so radioactive. Uranium-238 is a half-life of 4.5 billion years. Which means if you have 10 pounds, after 4.5 billion years, you'll have 5 pounds left of uranium-238, and you'll have lead and all sorts of other products. But it changes, and the actual element, only half of it is left. And Lynn even mentioned this, but the helium-3 from the sun has been hitting Mars, it's been hitting. It doesn't come to the Earth because we have a magnetic field that protects us from most of these charged particles. But if you look at the gas giants, Jupiter has helium-3 in its clouds.
It's vast.
Now, the problem with getting it from Jupiter is the gravitational field and the magnetic field is so powerful that you'd have a tough time getting a probe through the atmosphere. But if you go to Saturn, it's much less gravitational field. We can actually mine helium-3 from the gas giants and use it for further exploration. Now,
I'm sorry, you can mine it where?
The gas giants.
Gas giants, like, if you're a daredevil, you can do it in Jupiter, but it's a very hostile environment. But Saturn, I'm sure.
Neptune is probably the best.
Yeah,
But it's really
Neptune,
far.
A little ways away, yeah.
Yeah.
Now, if you think this is the height that we can go to fusion, in the article that's in yesterday's EIR, reprinted from '88, LaRouche is never satisfied. He goes, well, once we get to the asteroid belt, we're going to need more dense form of energy. Because the fusion, only 1%, less than 1% of those products, those fuel elements are converted to energy. There's something called matter or antimatter reaction. And a proton has a positive charge. An antiproton has the same weight, atomic weight, but it has a negative charge. Same charge, but a different sign. So if they come in contact, then 100% of the mass is converted to energy. So matter antimatter is the next step. But as Lynn says in that paper,
What is matter, antimatter?
So if you have a proton, it's positive charge.
Conventional matter.
Antiproton has the same weight and it's a negative charge. Now we use it. Is Belinda here?
No.
Okay, because she's an expert in all these MRIs. It's a PET scan. Anybody ever have a PET scan?
Positron emission tomography.
Yes.
Yeah, right.
Or it's different from a CAT scan.
Yes.
Where you scan, there's more than one way to scan a cat. But the PET scan, there are elements that are radioactive, but instead of spitting out an alpha particle, some of them spit out an electron, which normal matter electron is much lighter than a proton, like 1,800 times lighter, but it has the same charge but opposite signs. So the opposites attract. The positron, which comes out of some of these elements, like fluorine, different isotopes, it has the same mass as an electron, but it has a positive charge. That's why they call it a positron. Now, electron is matter, regular matter. Positron is antimatter. So it's the same mass, but a different charge sign. It's positive instead of negative. If a positron and an electron come together, they annihilate. And what happens is it's not enough energy to burn up your insides. But what happens with the PET scan is they give you this element that shoots out a positron. The positron hits the electrons in your inside, and it sends out a gamma ray at a certain energy level, and the detectors can detect that gamma ray signal, which is it's higher energy, higher frequency than an X-ray. But it's not enough of a dose to harm you on the inside, but they can detect it, so they can basically see what's going on inside without cutting you open. So that's the positron emission tomography, uses a positron. Now, we can make antimatter in these high-speed super colliders, like the one in Geneva, which some people thought was going to create a black hole and suck us all in, but we're still here. But what happens is you have enough energy, just like mass can be converted to energy, energy can be converted to mass. And if you have high-speed collisions, you can produce antiprotons. But the problem is you put in millions of times more energy in than you would get from the matter-antimatter reaction. So we have a long way to go before we can use that as fuel for a rocket. But what else are we going to do once we figure out fusion? We've got to have something to do.
So Joel, you said that the Princeton group is working with a helium-3, deuterium?
Yes.
How much helium-3 does it take to run that kind of an engine? I mean, if we have relatively small amounts on Earth, are they expecting that they're going to get it from mining the moon, or do they think there's enough?
Well, when we went to see Ben and Megan and I went to see, since he's near Princeton, we went to see his company, and we mentioned that the Harrison Schmitt had talked about helium-3 on the moon. And he knew all about it. He said, "Oh yeah, the Apollo astronauts were the first helium-3 miners." Now, in their experiment, there's very little needed. So they have run the experiment. And Mike, could you put up that inertial electric? You still have that?
Well, I have it here, but
In Wisconsin, where Harrison Schmitt was working with the head of the Fusion Technology Institute in Wisconsin, and they have what's called an inertial. Is it up there?
Not yet.
Oh. High-speed projector. But they have been running experiments using deuterium helium-3, and you can detect the product. You can detect the proton produced by that reaction, so you can tell how much fusion. Again, you're putting energy in to get a reaction, and you can detect the products of the reaction. Now, we're still at the point where the energy produced by the fusion is less than 1% of the energy you put in. But you can do a proof of principle. You say, well, I expect this much energy from this reaction, and you can detect that. And they've done that in Wisconsin and other places, and in the Princeton Plasma Physics Lab.
He's got the University of Wisconsin thing up. Is that what you want?
Okay, yeah. Is this the inertial?
Yeah.
You may have heard of these teenagers who have a fusion reactor in their basement or garage.
Bathtub.
So if you want one for your garage, you can have one of these. What you have is, can you see the spherical grid? There's two
Yeah.
spherical grids.
Yeah.
So that the inner grid has a negative voltage. The outer grid is close to zero. So there's a potential difference of minus, I don't know, does it have any numbers on there?
No.
Well, it's like minus 100,000 volts. Very low current. And you inject, this is a vacuum, so you have all the air stuff there. You inject deuterium and helium-3 or tritium, whatever your products are, into that chamber. And you energize the gas so it becomes ionized. It splits off the electrons in the nucleus. So the nucleus is positively charged. So if it's deuterium or helium-3, the nucleus, being positive, is attracted to the negative. And the negative is such a huge potential difference. Think of if you have a dam, and you have the height difference from the top of the dam to where your turbines are, is your potential difference. So your ions are flying to the center, and since it's spherical, they're crisscrossing, and enough of them collide and they fuse, and you measure the reaction products that come out. So when they're talking about a tabletop or garage fuser, this is what they're talking about. Now, the problem is you can have a good teaching device for fusion with this inertial electrostatic confinement. But because you have these grids in the center, some of your ions are going to be hitting the grid, so you're going to dissipate some of that energy. So it's very unlikely you get break even from something like this, but you can use it as a test. And you can use it as part of the civilian conservation corps to teach the basics about fusion. You could have the robotic club and the fuser club.
There you go.
So again, this is ongoing work in Wisconsin, other universities. But again, these are low intensity, low dollar programs that at the current rate of funding, you can look out in 50 years, if they keep the same funding, saying the same thing, say, boy, I wish we had that years ago.
Yeah.
But if you combine all of these theories and bring in the new students who may have a new idea of how to contain, how to use the torsion of the plasma to have a self-controlled vortex. And we can figure it out, just like we figured out how to hit the moon without splattering the crude onto the surface. You remember Don Cooper, who spoke at our meeting?
Yeah.
What did he say? He said, well, they told us we got to figure out the trajectory to the moon, and we had no idea how to do that, because you got the moon is moving, the Earth is moving, your spaceship is moving, and you have to hit it so that you're 60 miles above the surface, and then you go behind and you can't get help from Houston because the radio waves are high. So you have to specifically fire your engine so that you get captured in the moon's orbit. So they figured all that out.
Yeah.
And they figured out how to put a room-sized computer into a little shoebox that, compared to today, is still 60 or so kilograms. But that computer was able to calculate when to fire the thrusters so you can get into orbit, and when to fire the thrusters so that Neil Armstrong could just take over at the end and land precisely.
Right.
And I may have mentioned this before, but you hear all these comparisons. Oh, your iPhone has millions of times the memory and the computing power. Well, nowhere in the App Store do they have an app that can land you on the moon.
Right.
So the computer was designed specifically for that function. And it didn't exist. There's, at one time during the mid-60s, something like 60% of the output of the semiconductor industry, and it was just beginning at that time, was under NASA contract.
Huh.
Wow.
So the reason why we have iPhones and tablets today is because of the miniaturization that was begun with first the missile program, but it was accelerated by the Apollo project.
Any other questions?
Sheesh.
Thanks, Joel.
Thank you.
There was one statement from Shakespeare.
Oh, yeah?
I forget which play it was, but it goes something like this: helium-3 or not helium-3? That is the question.
Okay.
Whether it's nobler to suffer the slings and arrows of microgravity and cosmic radiation, or facing a sea of troubles like Prometheus with fusion and helium-3 conquering.
There you go.
I think that was the Tempest.
Thank you.
All right, Joel, thank you.
It was in Hamlet.
Was that Hamlet? Oh, yeah, it was.
That's it. Maybe it was on the Hamlet 2 sequel.
Oh, yes, Hamlet 2, sequel.
Yeah, for that
Yet to be created.
Yeah.
stuff in the
Grab
way
my
there.
He's
elbow
such a
and
big
I'll
hit.
steer you through this little sea of trouble here. There's some wires you just want to walk over. There you go.
Not to mention somebody dropped it.
Somebody
An
dropped an
eraser
eraser
and
and a marker. Can you
Oh,
imagine?
I thought Mike was going to pick that up. What are you doing,
I would
Mike?
think so, right? There you go.
Warmed up here.
Yeah. Well, you know, we have it on YouTube. Yes. I can send it to you. Yeah. So, how recently did you read it?
This was the baseball.
Yes, I'm gonna pick it up so it has a horn.
Fast office maybe? Yeah. Okay.
Chess ball.
Oh, yeah, yeah.
The grip
Yeah,
doesn't matter.
we've been doing this for a
Yeah, but
long
it keeps slapping.
All right.